Good day everyone. This video will tackle by the group of Kyla Arimado, Judy Ann Madre, Mika Espinosa, and Andre De Lomas. We will discuss our infographics about carboxylic acid. In these infographics includes description, structures, properties, synthesis, examples, and products of carboxylic acid.
Carboxylic acid description. Carboxylic acids are a class of organic compounds that contain a carboxyl functional group COOH. This functional group is composed of a carbonyl group C equals O and the hydroxyl group OH bonded to the same carbon atom, resulting in a highly polarized and acidic group. Carboxylic acids are commonly found in nature and play important roles in biological processes, as well as in various industrial and commercial applications.
Structures. The general structure of a carboxylic acid can be represented as RCOOH, where R represents a hydrocarbon group. The acidity of a carboxylic acid is due to the presence of the carboxyl group, which can be donate a proton to a base. The extent of acidity varies depending on the structure of the carboxylic acid, with the presence of the electron withdrawing groups increasing the acidity.
Properties. One significant property of the carboxylic acid is their ability to form hydrogen bonds, which leads to higher boiling points compared to other simple organic compounds. They are also capable of forming dimers through hydrogen bonding, which can further increase their boiling points. Carboxylic acids are also soluble in polar solvents due to their ability to form hydrogen bonds, but their solubility decreases as the size of the hydrophobic substituent group increases. Synthesize. Carboxylic acids can be synthesized through various methods, including oxidation of primary alcohols or aldehydes, hydrolysis of nitriles, and carboxylation of Grignard reagents. They can also act as both acids and bases, participating in reactions such as esterification, acidification, and decarboxylation. Examples: carboxylic acids are a class of organic compounds that contain a carboxyl functional group. One specific example of a carboxylic acid is acetic acid, which is commonly found in vinegar. Another example is citric acid, which is abundant in citrus fruits and used as a flavoring agent in food and beverages. The chemical structure of carboxylic acid can be visually represented through molecular diagrams illustrating the arrangement of atoms and functional groups. Products. Products made from carboxylic acids are vast and varied, including pharmaceuticals, polymers, fragrances, and food additives. For example, aspirin is derived from salicylic acid, a type of carboxylic acid, and is used as a pain reliever and anti-inflammatory medication. Additionally, many carboxylic acids are used as precursors for the production of esters, which are widely utilized in the fragrance and flavor industries.
I'm here to present about carboxylic acid. What's the connection between the smells of pit, underarms, vomit, and goats? Carboxylic acids. The smells of pit is partly due to the presence of isovaleric acid, which is produced by the bacteria living in your foot skin bacteria. Also turn odorless underarms secretions such as amino acid into carboxylic acid. The stench of vomit is caused by butyric acid produced by bacteria in our gut. Butyric acid is also found in rancid butter. That's where its name comes from. And it's a key part of aroma of Parmesan cheese. It's also added to some brands of American milk chocolate to give a tangy flavor. Yes, I basically just said that puke flavor chocolate exists and now it's going to haunt me forever. And these carboxylic acids take their common names from Latin word from goat's caproic acid and capric acid, pour in the small amounts in goat milk and produce a large amounts of the milk ages. They contribute to that goat stretch given these awful smells. You might wonder why we'd want to work with carboxylic acids at all, but we can actually some pretty nice smelling compounds using carboxylic acid as a starting point. And we can convert them into other awful compounds for organic synthesis. Let's kick off by reminding ourselves how we can make a carboxylic acid. For example, we can oxidize alcohols of aldehydes. Oxidizing agent. We can also make Grignard reagents. Reacting the Grignard reagent with carbon dioxide gives a carboxylic salt which can be protonated with acid to give a carboxylic acid. We can get more specific name for any carboxylic acid by looking at its structure using the number of carbons in the longest chain and adding the suffix oic acid. A carboxylic acid with 2 carbons is ethanoic acid. A carboxylic acid with 3 carbons is propanoic acid, and so on. So, in the previous reaction, we made 2 methylpropanic acid. Carboxylic acid have the highest priority among carbon containing function or groups. So, say we have a molecule containing both a ketone and carboxylic acid group. The carboxylic acid form the base name. We assign the carboxylic carbon the number 1 and the ketone gets a prefix, an example also known as ribulenic acid. At compound, use a starting point for the synthesis of pharmaceuticals and industrial chemicals. This compound, like we've mentioned, as a systematic IUPAC name and common name, like how ethanoic and vinegar has the common name acetic acid. As you'd expect, from all these carboxylic acid are acidic. If they have about 4 carbons or fewer, they can be dissolved in water. The hydrogen on the COOH of the structure will be partially ionized, forming a hydrogen ion and leaving behind a carboxylate ion. Specifically, carboxylic acids are weak acids because they don't release hydrogen ions in solution. As much as a strong acid like hydroxylic acid, thus the COH part of these structures allows intermolecular hydrogen bonds to form between the acid molecules or an acid and water. So carboxylic acids have high boiling point, and all of this with power than 10 carbons in a straight chain are liquids at room temperature. We can react shorter chain carboxylic acid with sodium or potassium hydroxide to form water. Soluble salt to the hydroxide ion grabs the proton from the carboxylic acid group, forming water and leaving a carboxylic can behind. In fact, even weak bases like ammonia can pull up a hydrogen ion and form like a carboxylic ion. As we formed earlier episode, but hydroxide ions and ammonia are good nucleophiles, which actually highlights an issue that can come up in the lab. Most basic nucleophiles tend to deprotonate carboxylic acid, so unlike aldehydes and ketones, we can't just use nucleophile to add groups to the carbonyl carbon. Here, we'll have to get a little creative with our chemistry before we tackle that problem. So let's look at source of the other reaction, carboxylic acids can be undergo. If we can't get back to an alcohol from carboxylic acid, we can use reducing agents such as lithium. Aluminum hydride, this powerful reducing agent, so after the reaction, we add proton source very carefully to react on any unreacted lithium aluminum hydride and give our alcohol a proton back. Another way to remove carboxylic acid group has a very straightforward name, decarboxylation. This involves healing the carboxylic acid and replaces the carboxylic acid group with a hydrogen atom. So, if we hit the heck out of almost and carboxylic acid, we can get it decarboxylate. And this reaction happens really easily when you hit compounds that have carbonyl group 1 carbon away from carboxylic acid group. However, sometimes you don't want to get rid of carboxylic acid group entirely, so there are also reaction to convert it into other functional groups. In fact, we can freshen up some of those smells by converting carboxylic acid into pleasant smelling esters by Fischer esterification. This is an acid catalyzed reaction of a carboxylic acid with an alcohol to form as ester. Ester are often day parts of the smells of flowers and commonly used perfumes. Fischer esterification can also classified as a type of condensation reaction. Because the two reactants kick out of water molecule when they have combined to get more as ester. Ester are often day parts of the smells of flowers and commonly used perfumes. Fischer esterification can also classified as a type of condensation reaction. Because the two reactants kick out of water molecule when they have combined. To get more specific first, the carbonyl oxygen grabs a proton from acid catalyst. Next, the lone pair of alcohol oxygen acts as nucleophile attacking the carbonyl carbon, disprotonating the hydrogen from the oxonium ion in that 1-2 punch of attack. Then, deprotonation, we're getting familiar with the OH group on the carboxylic acid finds a hydrogen ion from the acid catalyst, which make water a good living group with a little help from the neighboring oxygen atom. In the molecule, the water leaves, and finally another alcohol molecule from solution grabs the extra hydrogen on the carbonyl oxygen, giving us a ester and final product. All of these steps reversible, so the product isn't formed super efficiently